Okay, let's start the second hour, continuation of this. Now here, again with the same problem, I want to show another thing. So when we face a problem like this, if we first write down a parabola, that means we are experienced. We see that this will get different values along parabolas. But normally the first thing that comes to mind is to try straight lines. Okay? So again, consider f of x, y. So what was this? X squared y 4 over x to the 4 plus y 8. Okay? Normally, what comes to mind first is taking the limit along straight lines. Okay, all lines are straight, but we love to call them straight lines anyway. Okay, so try let y equals lambda lambda x. Okay, so who cares? Let us look at f x lambda x. So this is lambda 4 x to the 6 over x to the 4 plus lambda 8 x 8. Okay, so I hope I'm doing this correctly. That's 8 power, that's the 4th power. I have 2. Okay, so this is it. Again, along the limit. Okay, so the point here is, this is the point. This is different than 0, 0. So this means that x is different than 0. So I can cancel x to the power 4. Okay, so this is lambda 4 x squared over 1 plus lambda 8 x 4. Okay, so now I take the limit as x goes to 0. The limit is 0. Okay, so limit as x y goes to 0, 0, but restricted to the path lambda x of x y is equal to limit. Now we come here, we take the limit as x goes to 0 of lambda 4 x squared over 1 plus lambda 8 x 4. Okay, so this is a polynomial in x. This is a polynomial in x, and it doesn't vanish when x equals 0. So this is a nice continuous function. I can plug in x equals 0, and I get 0. Okay, so limit along any line is 0. Okay, so this doesn't tell us anything, as I explained before. Along two different paths, we calculated that we get the same limit. So it doesn't tell us that actually the limit exists. So you see that in this case, we know the limit does not exist, but then there are paths along which we get the same limit. Okay, so this gives no information. So normally you start by checking the limit along straight lines. If you get the same limit, okay, so it doesn't tell us anything. Next, you try parabolas, then you try cubes. Depending on how the formula, how the expression for f is given, maybe you get 0, 0 up to a certain degree, where you move along the path y equals lambda times x to the 7 or something like this. Then you find that the limit depends on that lambda. Then you know that the limit does not exist. Okay, so let me do another simple example here. The simple example is, of course, x, y. So another simple example is this. Limit x, y goes to 0, 0 of x, y over x squared plus y squared. Okay. Now again, we cannot plug in x equals 0, y equals 0. So somehow we suspect that the limit does not exist. Okay, so how do you suspect these things? If you solve lots of problems, which you should do, then you get a feeling about these things. Sometimes your feeling is wrong, sometimes it's correct, but you cannot solve a math problem blindly. You must have an expectation. You should spend 30 minutes, seconds, 60 seconds, something, staring at the problem and making a guess. It doesn't matter if the guess is correct or wrong. Okay, so the important thing is you have a guess. Now you try to show yourself that your guess is correct. Along the way, you will learn a few new things. Maybe you will change your guess. Okay, but after you change your guess, now again you have a guess. You have to do your calculations in a purposeful way. Otherwise, you see all these algebraic techniques you can apply one after the other, and it doesn't go anywhere. Okay, so here we suspect that the limit does not exist. If you suspect that the limit does not exist, how many techniques do we have? Okay, sometimes when you are listening to calculus, you get the feeling that there are millions and millions of different theorems, and which one you will remember in the exam or in real life. If you think about this, there are not many. Okay, how many techniques do we have to show that a limit does not exist so far? Well, two-path test. So what's the simple path? A straight line. So let's try straight lines. Okay, so try two-path test. Let y equals lambda x. Okay, then x squared plus y squared restricted to y equals lambda x becomes lambda x squared over x squared plus lambda squared x squared. Okay, since x is different than 0, we are taking the limit. So I keep repeating this so that it becomes natural. We are on the punctured disk. The origin will not enter into calculations. Okay, the origin will be the point corresponding to x equals 0 here because we tied y to x. Okay, so then x squares can cancel. We have lambda over 1 plus lambda square. Okay, so if you move along this line with slope lambda, at the limit you will get this thing because now this is a constant. Limit of a constant is equal to the constant no matter where you are taking the limit. Okay, so limit of xy over x squared plus y squared as xy goes to 0, 0, but y is restricted to lambda x is equal to okay, xy goes to 0, 0, and y is restricted like this is the same thing as x going to 0. So this is now limit x goes to 0. We simplify this part. We have this lambda over 1 plus lambda square. So you see that x doesn't appear here. So this is lambda 1 plus lambda square. Okay, so this is algebra. We put a full stop here. Okay, now what did we do? Now we start thinking. Okay, so when you are doing algebra, you don't do any thinking. You decide the technique, you apply the technique, there is an outcome. Now, what does it mean? If we move along different paths, we get the limit depending on the slope of the path. So if you change the path, you'll get a different number. Okay? So along different paths, we get different limits. So the short way of saying that the limit depends on the path. However, if the limit existed, the limit does not depend on path, so the limit does not exist. So the limit does not exist. Now, going back to your friend's question last hour, you see that this thing will change this time between minus 1 over 2 and plus 1 over 2. And if you plot the graph, you'll be convinced that these are the only numbers that the surface hits the z-axis above the origin. And then once you are convinced with this, then you can show that the function does not take larger values than this or smaller values than minus 1 over 2 at the origin. Okay, so there is another test which goes by Serto's theorem, because I started this as a joke, but then it caught on. Now we keep calling this Serto's theorem. I discovered this while I was trying to prepare a challenging homework problem, because if you look at the problems in the book, all of them can be solved by squeeze. If the limit exists, you can always show that it can be proved by squeeze theorem. And if you can prove it by squeeze theorem, it means that one of the powers of these x and y is large. Okay? So you take it out, you squeeze everything by that power, the limit is 0. So if you take all the powers small, so that none of them will squeeze the whole thing, certainly the limit either exists or not. There is no third possibility. So which one is which? Okay, so in order to discover a nice homework, I discovered this rule. So now I'll talk about this rule. But let us first of all give an example where squeeze theorem immediately tells you that the answer is 0. Okay. So another example is this. Limit. Okay, so x, y goes to 0, 0. Let's invent something. X to the 4, y square, let's say. Okay, I want to take x square plus y. Okay, let's say x to the 4 plus y, y 6. Maybe it works. Okay. So notice that I take this thing. This thing is, so let's write this x to the 4 y square, x to the 4 plus y 6. I write it as y square, okay, times x to the 4 over x to the 4 plus y 6. So you see that now instead of y square, I could write anything here, y cube, y, just y, anything. Now the observation always given in the book is that this thing is less than or equal to 1. Okay, so this is less than or equal to 1. So the whole thing is less than or equal to y square. If instead of y square I have y cubed, then I'll consider the absolute value of this. This thing is always less than or equal to y, so this thing would be the absolute value of y cube. Okay, so now this in our example everything has even power, so this thing is already positive. Now we apply the squeeze theorem as x, y go to 0. Okay, this is constant, it always goes to 0. As x, y go to 0, y square obviously goes to 0. Okay, so therefore our function goes to 0. Remember that this notation means that, this picture means that we applied the squeeze theorem. Okay, so by squeeze theorem, our function, we have limit x, y goes to 0, 0 of x to the 4 y square over x4 plus y6 is 0. Okay, so this is the technique that applies to most of the exercises in the book when you can have one power matching here. So you just take out something which obviously is less than or equal to 1, and something here, which is, this part is a product of x's and y's. Okay, so then that goes to 0. Okay, so let's look at the general case where if I take these numbers, you see if instead of 4 I had 3 here, then I cannot do this. You cannot take y square out, and you cannot take x4 out, and y square over this thing, I don't know if it is less than or equal to 1, because when absolute value of y is small, then y square is larger than y to the power 6. So these arguments become complicated. Okay, so our next result is the following. So you can call this finger counting. So another method. Okay, so we look at limit xy goes to 0, 0 of x to the power a, y to the power b, divided by x to the power 2m plus y to the power 2n. Okay, so here a, b are integers. One of them can be 0. Maybe this is x to the power 7. I don't see why. That's possible. But here in the denominator, we want a polynomial which vanishes only at the origin. So the easiest way is to have even powers. So that's why we have 2m, 2n, emphasizing that we have even powers there. And these are strictly positive, because if I don't see this, okay, then it vanishes when x is equal to 0 and y is free. So it vanishes on a whole axis. So these are positive, and they are also integers. Okay, so this limit is equal to 0 if and only if a over 2m plus b over 2n is strictly larger than 1. Otherwise, the limit does not exist. Otherwise means that 2m plus b over 2n less than or equal to 1, the limit, so 1 is also a bad case, the limit does not exist. Okay, so this gives us the surprising result that the limit cannot be anything. If the limit exists, it's going to be 0. So either it is 0 or not, and it's all encoded in here. You just look at these numbers. So how do you suspect that something like this will hold? So here you see this is a typical L'Hopital case, but in L'Hopital we are looking at graphs of one variable function. So there are two paths, okay? So one of them is the numerator, one of them is the denominator. They are fighting. They are both going to 0. But if one of them goes to 0 faster than the other, then whatever he says holds. If the denominator goes to 0 faster, then the limit is infinite, plus or minus infinite. I'm talking about one-dimensional case. If the numerator is faster, then the limit is 0. If they agree at some point in between, then we can get a different limit. So that holds in one-dimensional case. In order to formulate this, what are we talking about? We are talking about their speed of approach to the origin. That's derivative. Okay? But now here we have two different variables. We don't have a curve, we have a surface. How fast is the surface approaching the origin? Well, it depends on which angle you are looking at. It depends along which path you are measuring. So there is no unique way of applying L'Hopital. So I'm sure that in the exam, when you panic, you take the derivative and derivative of the numerator and denominator with respect to some variable. Okay, so it doesn't make any sense. You get some number, but it has nothing to do with the actual result, because of the thing I am explaining. We have surfaces in this case. If we have 3 parameters, then we are talking about a solid, which is a graph in R4. We don't know how to draw that. So L'Hopital does not make sense here. Okay, so you have to think in a different way. So these guys are trying to go to 0. These guys are trying to go to 0. Okay, so how fast they are going to 0 depends on these integers. So there must be a formula which compares their speed. Okay, so it turns out that if you play with this, you can read this on my webpage. I have 2 different proofs. I have one proof, but a friend of mine suggested that we can use Lagrange multipliers, which we will do towards the end of this chapter. So you can prove this in a general case. But this is how it turns. You see that these a and b tell how fast the numerator is going to 0. These 2m, 2n tell us how fast the denominator is going to 0. So if the numerator is going to 0 faster than the denominator, the limit is 0. So that's how you remember these things. So going back to this example, for example. Okay, so example, we had this x4 y squared over x4 plus y6. Okay, so we have 4 over 4. Well, we already have 1 here, plus 2 over 6. You see that this is larger than 1. So the limit is 0. Is 0. In these cases, when we talk about the limit, obviously here we are interested in the limit as xy goes to 0, 0. Okay? The limit of this at any other point is just the value of the function at that point, because this is defined, so it's a continuous function. You just plug in the value. Okay, so this also holds for three-dimensional things. So in any dimension it works. So let me mention that. Okay, so we had xy over. Okay, let me also do this one. We had xy over x squared plus y squared. Okay, so we found that the limit does not exist by two-path test. We can also do this here. So this is 1 over 2 plus 1 over 2. So this is equal to 1. It is, well, either you say it is not larger than 1, or it is this case. The limit does not exist. The limit, so as xy goes to 0, 0 does not exist. Okay, so let me check if I have other examples here. Okay, so let me also give the three-dimensional version. This works in any dimension, but just for the convenience. Also, if we have limit x, y, z goes to 0, 0, 0, x to the a, y to the b, z to the c over x to the 2m plus y to the 2n plus z to the 2k. Here a, b, c integers, m, n, k positive integers. So this limit exists and is equal to 0 if and only if. In mathematics we are lazy, we use this notation to say that the argument works both ways. If you have this, then you have this, and you have this, you have this. If and only if a over 2m plus b over 2n plus c over 2k is strictly larger than 1. Obviously, this part is easier to calculate, so we always use it in this way. If this is larger than 1, we know that the limit exists. Otherwise, the limit does not exist. Of course, this sentence is superfluous because the statement is already implying that. Okay? If the limit exists, then you have this result, and you have this result, the limit exists. So if any of these conditions is violated, the other part is also violated. That's also already inside the theorem, but we write these obvious explanations to remind ourselves what to do. Instead of thinking for a split of a second, the result is already here. Okay? If it doesn't hold, the limit does not exist. Okay, so let me check. Okay, so let's give an example where this doesn't directly apply. Okay, so let me make a remark here. So remember that in the last semester in one-dimensional calculus, you were asked to calculate certain limits, and there's a note saying don't use L'Hopital. Okay, so don't use L'Hopital means that in your solution, don't refer to L'Hopital. But on the back of the page, you apply L'Hopital and you find the limit. Okay, so you find that the limit is 7. Okay, now you go back, knowing that the limit is 7. You use the techniques that you are asked to demonstrate your superiority in. You show that the limit is 7. So similar things hold here. Okay, if there's a remark in the exam saying don't use Sartor's theorem, so you are not forbidden to use it. You use this to check if the limit exists or not. Okay, then what does the question want? The question probably wants you to use squeeze theorem. Can you find something which squeezes this? Okay, so now that you know the limit is 0, you can definitely find it. Okay, what makes it difficult is if you have a doubt whether the limit exists or not. Okay, half of the time you are trying to check if the limit exists, and half of the time you are trying to show that it is equal to 0. Just to gain time, you apply these things. Okay, so that's what it means. Don't use a certain technique. Okay, you use a technique, you find the answer, then you go back and answer the question along the line required. Okay, so sometimes it's not straightforward that this theorem can be used. So let me invent a problem, another problem. So let's look at limit as xy goes to 0, 0. Let's say x square. Then here let me write sine to the 4 divided by, now here I want x to the 4 plus y 8. Let's say y 8 or 6. Okay, let's say y 6. Okay, so you see now you cannot directly apply this theorem. Maybe you can find, you see squeeze theorem is not easy either, because I deliberately chose these numbers small so that a squeeze theorem is not obvious. But you can play the following trick. This is the same thing as limit xy goes to 0, 0 of x squared times y to the 4 divided by x to the 4 plus y 6 times. Here you see this is a nice thing about mathematics. You can always do whatever you like here and then you pay a price. Well, that's also the case in real life. Okay? In real life you are free to do whatever you like, but after you do it there's a price. Okay? So now we pay the price. What did we do? We multiply by y to the 4, so we divide by y to the 4. We have sine y4 over y to the 4. Okay, so now you see life is easy because we have product of limits. So this is x squared y4 over x to the 4 plus y 6 times limit x y goes to 0, 0 of sine y4 over y4. Okay, now we check. This part is easy. Okay, so this limit is equal to 1. We all know that sine t over t as t goes to 0 is 1. Okay, so this part now we check. Okay, now you can apply this rule immediately. Okay, let's check 2 over 4 plus 4 over 6 is 1 over 2 plus 2 over 3. So this is 3, 7 over 6, strictly larger than 1. So this limit is 0. Okay, so limit of a product is product of limits. 0 times 1 is 0. 0 times 1 is 0. Okay, so this is one way where you tricked the problem and brought it into two parts, both of which you can trivially handle. Okay, so let's see if I have another thing. So I have one with tangent. Well, let's do the one with tangent. That's also easy. So I have x squared y tangent. So another thing. So one question. So when you have tangent, tangent is sine over cosine. Cosine doesn't cause any problem at the origin. It is 1. So again, it is sine. And we'll play the same trick with sine. So let me, since I did it at home, so probably it will work nicely. So limit x, y goes to 0, 0 of I have x squared times y tangent y over x to the 4 plus y squared. Okay, so let's see. I'll have, well, this limit should be very easy, but okay, let's write this. Now this is limit x, y goes to 0, 0. I try to break this into parts. So I'll write this as x squared y squared over x to the 4 plus y squared times sine y over y. Okay, so you see I multiply this by y, dividing by y, and I'm taking tangent as sine over cosine. I take the sine here, and I have 1 over cosine y. Okay, so I'm taking the limit of this. Okay, so now you see it is easy. This part I have 2 over 4 plus 2 over 2 is way larger than 1. So that limit will be 0. So this limit is 1. And this is continuous at the origin. Cosine 0 is 1. So here value at 0 is 1. So this limit is 0 times 1 times 1, 0. Okay, so you can now invent different problems. Okay, the way to check by yourself whether you understand the theories to cook up some exercises for you. Okay, so you have to cook up some problems which are not Mickey Mouse and which are not impossible. If you can cook up a reasonable question for yourself, then it means that you understood the problem, you understood the theory from all angles. Okay, so try a few things. For example, instead of tangent, you can have 1 minus cosine of some polynomial, and then arrange that. You see 1 minus cosine divided by the parameter will go to minus 1 over 2 or plus 1 over 2 something. Okay, so you use those things. Okay, so I think we covered these. Okay, so I think that's the end of this section, limits and continuity. Before I pass to partial derivatives, are there any questions?
Can we solve this question by using theorem?
No, now we know, let's do this way backwards. Now we know that the limit exists. Okay? Now, so that whichever path you use, you'll get 0. Okay? You use 2 different paths, you get the same value. You cannot conclude anything from that. We are saying that whichever path I try, I get the limit as 0. Okay, but we look back at the definition of limit, there are no paths. It says that take a small neighborhood, all the points here will be mapped into some epsilon neighborhood. You didn't do that. You are taking only spatial things. Remember the example about the streets being wet. Are the streets wet because it rained or because the gardener was generous that day? Okay, so it doesn't work that way. If some nice thing happens, if the limit exists, then we get the same limit along every restricted case. But if along restricted cases you get the same thing, you don't know if you are going to get the same limit when you remove the restriction. Okay, so if you look at it as restriction, then maybe it's a feeling, then you start feeling that way. But if you find 2 paths where the limits are different, then you immediately know that the limit does not exist. Okay, so any other questions? Generally, we go to the pharmacy and we want to buy something and we are afraid. We say, I'm going to buy this for my friend. So do you have a friend who didn't come to class, but if he came, he would ask something? So does anyone want to ask a stupid question that your stupid friend asks? If you don't ask stupid questions, then there's no fun in calculus. Okay? The whole fun in mathematics is you suspect that something is correct. You try, it turns out to be wrong. You are surprised. If everything works nice, then who wants to do this boring thing? Okay, so think about these things. If you have questions, well, I prefer you ask them in class. But if not, you can come to my office. But that's also some hard work. You have to climb stairs. The easiest way is to send me email. The advantage of this is because if I find the question difficult, I will not be embarrassed. I'll pretend that I didn't see the question for an hour, and then suddenly I see the question. So I will take an hour to find the answer. And for you, the nice thing is if you formulate your question, then 99% of the time, by the time you finish your question, by the time you finish asking the question, you'll see the solution. Okay, so that's almost what happens every time. Okay, so when you are writing an email, you are trying to formulate it so that the stupid professor will not misunderstand you. But when you are that careful and you formulate the structure, then you see, because the answer is there. Okay, that happens to us a lot of time when we were grad students. We would go to our supervisor, try to ask him a question, but you have to ask this carefully because this old guy may not understand it. But by the time you are in the middle of the question, you see the answer, and you suddenly leave the chalk and run to your office to write the answer before you forget it. And your poor supervisor leans and says, glad to be of some help. Okay, that's the only thing he says all day. That's something very typical. Okay, formulate your questions. Try to write emails to me. Okay, so most of the time you'll find the answer yourself. If not, then I'll take a few hours, find the answer, and write to you. Okay, now let's pass to the next topic where we will do partial derivatives. Okay. So then this is a section on partial derivatives. So we have function of several variables. Let us start with the two variables. Okay. So the partial derivatives is the same idea as one parameter derivatives. We are extending it to several variables. If you have a function of x, we know how to take the derivative of it with respect to x. If you have a function of x and y and z and w, okay, then we will come to this. There is a way to talk about it being differentiable. But first, the easiest thing to do is consider this as a function of x only. Take its derivative with respect to x. So wherever you see y, z, w, those things are all constants for you, constants with different names. Okay, so that's partial derivatives. So first of all, write the definition for two variables. Okay, so we have a function of x and y. So we have f of x, y. Okay, defined around x sub 0, y sub 0. Okay, so this time the function is nice. Okay, so it has values there. So we talk about is the partial derivative of f of x, y at x sub 0, y sub 0 is. Okay, so forget about y. We have a function of x defined around x sub 0, the derivative of f of x at x sub 0. Okay, so this is what we want to do. You just take the derivative with respect to x. So formally, when we write it, is this limit as x goes to x sub 0. Okay, so remember now we will write the usual limit quotient. Here we are treating everything as constant, so only x will change. So x goes to x sub 0 of f of x minus f of x sub 0. So I'll put something here, divided by x minus x sub 0. Okay, so what do I put here? So here it is clear that I should put this y sub 0. Now, what do I put here? I have to put here something. So remember in the one-dimensional case, when I send x to x sub 0, this thing, okay, so this thing goes to f of x sub 0, so that this is 0 over 0. And if the limit of that ratio exists, that's the derivative. Okay, but suppose nobody is looking, so when we are taking the limit, you just put x equals x sub 0 there, then this thing should be this thing. Okay, but I have y sub 0 here, so I'd better put y sub 0 here. Okay, so the limit is this thing. Of course, we know from last hour that sometimes limits exist, sometimes they don't. So if this doesn't exist, we don't say that the derivative of this is some limit which doesn't exist. Who wants it? So we just put a comma here when the derivative exists, when the limit exists. Okay, so just like in one-dimensional case, some functions have a derivative, some don't. Okay, so if this exists, we call it the derivative of f at that point. Notation, derivative of f with respect to x, we put these curly d's. This is d, but curly d to denote that there are other variables floating around. And this is calculated at x sub 0, y sub 0. Okay. So this is just like, again, one-dimensional case. You don't plug in these numbers here first and then attempt to take the derivative, because when you plug these in, you get a constant. You take the derivative, you get 0. Okay, so it's just the same thing as in one variable. First, you take the derivative. Then, after when it is finished, you put these numbers in. Okay, so in practice, so let me say similarly, derivative of f respect to y evaluated at this point is equal to limit. This time y goes to y sub 0, okay, in this case. So here I have x sub 0 is fixed. I have y, f of x sub 0, y sub 0, divided by y minus y sub 0 if the limit exists. If the limit exists. Okay, so this is the algebraic thing. So let me do one more algebraic thing, then we'll take we'll start drawing pictures. It will be more entertaining with pictures. Okay, so the yoga of this. So how do we implement this? Into calculations. Okay, so for example, this part, you see that you are not touching y at all, and when you have a function of x only, okay, you take the derivative respect to x, and then you put x equals x sub 0. So we can do this generically, okay, so x goes to some point of this, so y, I can take f of x y equals, let's say, x squared y cubed plus y to the 70 plus 1. Okay. Now, if I take derivative of this with respect to x at an arbitrary point, okay, so I'll take the derivative and then I'll put this number, but the number is generic. Okay. So this is, the definition says that y is constant, only x is changing. So we use just what we learned last semester. The derivative of this is 2x y cubed. Y cubed is a constant, so it stays there. Plus, this is there is no x in it. There is no x in it, so that's it. Okay. So we take the derivative of this with respect to y at x y. Now here, this is a constant. So a constant times y cubed, I take the derivative with respect to y. This is y constant y squared plus this is y. So this is 70y 69. Well, this is constant. This is it. Okay. So to give this generic point here, you see it will not be nice here to say that x goes to x. So what we do here for this one, we use derivative of f respect to x at the generic point is limit as delta x goes to 0 of f of x plus delta x y minus f of x y divided by delta x. And similarly for this one, so similarly for derivative of f respect to y at x, y. Okay, so this is just to change the notation so that we don't bother here asking when we put the numbers in actually. Okay, so this is the general description. Of course, if the limit exists. Okay, so this is the mechanism of this. If you have a function of several variables, you decide that only one of them is changing, the others are just staying there and watching you. You take the derivative accordingly. All the other variables are just constants. Okay? So what is the meaning of this? Obviously, algebraically, we can do this. But what is the meaning of this? The meaning of this is tangent lines. Herkes kıpırdanmaya başladığına göre. Okay, so on Thursday morning, I'll draw pictures and I'll show that these are slopes of lines, tangents to the graph at that point. Okay, thank you.